In this video, you will learn to use the binomial theorem to find a particular term of a binomial expansion. Now what the binomial theorem is it's a theorem that tells us how we can expand a binomial raised to a certain power. So if you're given a plus b to the n power, the binomial theorem states how we can expand this. Now what I'm about to show you is going to look very complicated, and it does look complicated, but with examples I think it won't be quite so bad. Alright, and so what we have here is basically a pattern of each term. So we start with a to the n power, so whatever power we have, whatever exponent we have up here, we raise a to that power to begin with. Alright, and then if you look at the variable component, okay, the exponent for a will keep decreasing. So whatever the first one was, the second term will have an exponent 1 less than that. That's where the n minus 1 comes from. And then if you look here at the variables, the exponent again with a would be now n minus 2. And then we have here in the third term n minus 3, etc., until we get to the end where there's no a's. So a to the 0 power, which would just be 1, which is not needed to be stated. And then if you look at the b's, so the variable b. So for the first term right here, there are 0 b's. And then the first term, or second term, sorry, we have b to the first power. And then the third term, we have b squared. And then we have b cubed. And that keeps going until we reach the last term. And that will be b to the n power. So whatever the exponent was up here, that's what the exponent will be for the last term. Now, the coefficients, this has a pattern as well. All right, so if you look the coefficient here in the front, the number in the numerator will always be n factorial. So we notice the exponent up here for the binomial was n. The factorial is going to be n factorial. All right, and then here in the denominator, we take the exponent with the a, make it a factorial, so n minus 1, make it a factorial, and then the exponent with the b, make that a factorial. So we have 1 factorial. And then here for the third term, we have, again, n factorial on the top, and then in the denominator, we have n minus 2 factorial because the exponent with a is n minus 2, and then the exponent with b is 2, so that's going to be a 2 factorial as well. And that pattern is going to continue. So the exponents with a and b for the next term is n minus 3 and 3. So in the denominator, we have n minus 3 factorial times 3 factorial. All right, and you might be wondering, well, what about the first term and the last term? Why is there nothing factorial stated there? Well, there is, but things will cancel out. So like the first term, for example, if we're keeping this pattern going, this coefficient would be n factorial over, and then we take the exponent with a, make it a factorial, so that'd be n factorial, and then we do the exponent with b. So there's no b, or b to the 0 power, so that would be 0 factorial right there. All right, and so the n factorials would cancel out. 0 factorial is the same thing as 1, so what we have is 1 over 1. So the coefficient is going to be 1, but it's not needed to be written. So the pattern does continue and does work for the first term, and the same idea for the last term as well. So as you expand with a certain exponent, it's probably easiest if you work with the variables first. So get this component first for each term, and then from there, once you have that, then the coefficient is found by looking at the exponents with each of those variables. So that's my recommendation, but you can choose to expand how you like as long as you're following this pattern. Now let's take a look at our first example. We have a plus b to the 14th power. All right, so we're going to expand this, and we don't want to maybe do every single term, but at least get us started. So for this one, okay, you begin with a to the 14th power. That's your first term. And then from there, you're going to decrease the exponent with a. So the next term is going to have a to the 13th power. And then we have b to the first power. And it's b to the first power because the first term had 0 b's. Second term will have 1 b. And then the next term will have a to the 12th power. And then b squared. And then the next term after that would have a to the 11th power. And then b cubed. And etc. This pattern would continue. And by the way, notice that the exponents with the variables will always add up to be whatever this exponent was. So since the exponent is a plus b to the 14th power, your exponents for each term should also add up to 14. And we see that is the case. A to the 14th power, here we have 13 and 1, here we have 12 and 2, and then we have 11 and 3. Each of those exponents will add up to be 14. And then from here, the question is, what will be our coefficients? So the coefficients, the first term would just be a 1. Second term, we have 14 factorial over, and then we look at the 13 and the 1. So we do 13 factorial and then 1 factorial. All right, and then the next term is 14 factorial again on the top. Denominator would have now a 12 and a 2 factorial. So 12 factorial and then 2 factorial. The next term, again, will have it's going to have a 14 factorial. And then we're going to have in the denominator 11 factorial and a 3 factorial. All right, and this pattern will keep on going till we reach the end. And the last term is going to be b to the 14th power. So here in the notes, we see all that typed up. And if you look here at this line, that is what we have. All right, we also added actually one more term here. We have a to the 10th power, b to the 4th power, and then the coefficient for that would be 14 factorial over 10 factorial times 4 factorial. All right, so this is what we have, and we can simplify that coefficient. So that'll be our last step here, is to simplify. So to simplify, what we have is for the first factorial, so 14 factorial over 13 factorial. I guess make sure you know how factorial work. So we're assuming you know what factorial means, but remember that 14 factorial means we have 14 times 13 times 12 times 11 times 10, etc., all the way down to 1. And then same thing for 13 factorial. We have 13 times 12 times 11, and that keeps going all the way down to 2 times 1. All right, so that is what factorial means. Now you want to get pretty good at this because you don't want to have to write this out every time, but realize that with factorial, if there's a factorial on the top and the bottom, that at a certain point, these different numbers will start canceling out. So we see here the 13s will cancel, 12s will cancel, 11s, 10s, etc., all the way down to 2 times 1. All that will cancel, and you're left with simply a 14. So that coefficient here for the second term is going to be 14. All right, then you do the same thing for the following terms. So the next one, we have 14 factorial over 12 factorial times 2 factorial. So again, you want to make sure you can start doing these pretty quickly in your head. And we can realize that 12 all the way down to 1 will cancel out with factorial. Because 14 factorial is 14, 13, 12, 11, etc., all the way down to 1. The 12 factorial is 12, 11, 10, etc., all the way down to 1. So notice that the 12s, 11s, 10s, etc., all the way to 1 will cancel out. You're left with 14 times 13. But don't forget, you also have the 2 factorial down here. So 14 times 13 over 2 factorial, or 2 times 1. All right, so then 14 over 2 is 7. So we have 7 times 13, which gives us 91. So the coefficient there would be 91 for that third term. Let's do one more term to get a little more experience with that simplifying. So here we have 14 factorial over 11 factorial, 3 factorial. All right, so for this one, we have 14, 13, 12, 11, etc., all the way down to 1. 11 factorial is 11, 10, 9, etc., all the way down to 1. So for 14 factorial over 11 factorial, the 11 all the way to 1 will cancel. So you're left with 14 times 13 times 12. But don't forget you have the 3 factorial also, which is 3 times 2 times 1. Well, 3 times 2 is 6, and then 12 on the top will divide with 6 in the bottom. So 12 divided by 6 would give you 2 on the top. So what we have is 14 times 13 times 2. And when you multiply those together, you get 364. So the coefficient for that fourth term would be 364. So if you did this all the way, we would have to do the same process for all these different terms. So there'd be, 15 terms? So you have to do that 15 different times to find the coefficients. And by the way, it would be 15 terms because here the exponent is 14. And if you think through how the variables work, all right, if you look at the b's, for example, this first term has 0 b's, then we have 1 b, 2 b's, 3 b's, 4 b's, and at the end it's going to have 14 b's. So the b's go from 0 to 14 for the exponents. Even for the a's, we start with 14 and go all the way to 0, 14 through 0. So the last term has no a's. So if you start counting from 0 through 14, 0 would be 1, 1 is the second number, 2 is the third number, and you count, there's actually 15 different terms. All right, so that would be the case as well for any expansion. The number of terms is 1 greater than the exponent. So to finish off this problem, we have stated right here the pattern that we would see. So if you put in all those coefficients, we have a to the 14th plus 14 a to the 13th power times b plus etc. And this would keep going like we said for 15 terms total. Example 2, we have pretty much the same type of question as with example 1, except here the exponent is 18 instead of 14 like we had for example 1. And here we're told just to find the first 5 terms. So we're not going all the way to the end, we're just finding the first 5 terms. Now, what I think to be the simplest way to begin is, as I stated, we can start with a to that 18th power. That's going to be your first term. And then from there, each term, the exponent for a will decrease by 1. All right, so the next term would be a to the 17th power, and then from there would be a to the 16th power, 15th power, etc. And then the b's, we are increasing. So we start with 0 b's, then we have 1 b, and then we have a to the 16th power, so we decrease a by 1, and then increase b by 1, so we get b squared. So now we have 3 terms. Keep this pattern going. So we now have a to the 15th power. Then we'd have b cubed. So that'd give us 4 terms. And then we have a to the 14th power, b to the 4th power. And again, we know we're doing this correctly with the exponents and the variables because if you look at the exponents for each term, it's going to always add up to be 18, this number right here. All right, now at this point we need to figure out what the coefficients are going to be. So the coefficients you find by looking at this exponent right here and then the exponents with the variables. So the numerator for each of these different coefficients will be 18 factorial. So you can write that right in if you want. 18 factorial goes on the top for each of these. And then the denominator we find by looking at the other exponents. So for the second term here, we have a to the 17th power, b to the 1st power. So we have 17 and 1 as our exponents. So we have 17 factorial and 1 factorial. The next term we have 16 and 2 for our exponents. So we have 16 factorial and then 2 factorial. The next term we have 15 and 3. So we have 15 factorial and then 3 factorial. And then the next term we have 14 and 4. So we have 14 factorial and 4 factorial. And that is what we see typed up right here. And actually, we see that on this next part. All right, so right here. Okay, so from this point, now we just need to figure out how do we simplify each of these different coefficients. So again, you want to be able to do a lot of this in your head. So for this one, realize that factorial means we have 18, 17, 16, 15, 14, all the way to 1 multiplied. 17 factorial is 17, 16, 15, all the way down to 1 multiplied together. So if you look at these, the 17, 16, 15 for top and bottom will cancel out, and you're left with simply an 18. So we have 18 would be what that would simplify to be. So that would be 18, and then we can carry on with the next one. So for this one, if you can think through what we have on the top, we have 18, 17, 16, 15, 14. 16 factorial is 16, 15, 14, all the way down to 1. So what you're left with when things cancel is going to be 18 times 17 in the numerator. All right, and then we still have the 2 factorial to take care of. So that would give you 2 times 1. And by the way, if you're struggling to do this in your head, you could just write everything out and then just cancel. But it's going to be much better if you can start doing this in your head a little bit. All right, so then from here we can simplify. 18 divided by 2 is 9. So we have 9 times 17, and that would give you, what, 63, carry the 6, would be 153. So the second term, or the third term, sorry, would have a coefficient of 153. Now this next term right here, we would have 18 factorial and 15 factorial. If you can visualize that, that's going to cancel out the 15s all the way down to 1. So you're left with, in the top, just 18, 17, and 16. And then the denominator, the 15 factorial, cancel with all the 15, 14, 13, etc. with the top. So you're left with a 3 factorial, or 3 times 2 times 1. All right, so then from here, you can simplify. And when you simplify, and you multiply all that together and divide, you're going to get your number, which would be 816. So this term would have a coefficient of 816. By the way, notice a pattern emerging as well with these numbers right here. So if you look here at this row, this first one, you can imagine that as being 18 over just a 1. So notice the pattern in the numerator. We can kind of pick up on this pattern to get the next one. You see how we started with 18, now we have 18 times 17, then 18, 17, 16. Keeping that pattern going, you would have 18, 17, 16, and 15 all in the numerator. And the denominator, you look at the pattern, we have 1, and then 2 times 1, then 3 times 2 times 1. So keeping that pattern going, we would have 4 times 3 times 2 times 1. And you can confirm that if you take this right here, 18 factorial over 14 factorial times 4 factorial, and you cancel things out. This is what you would get. And then when you multiply and divide, you should get 3060 for this coefficient. So these are the coefficients for each of those terms. And you put it all together, and your answer would be right here. This is the first 5 terms of that binomial expansion. All right, so now we've seen the pattern, we've seen how to expand. Now in the next example, we're going to find a specific term within an expansion. So instead of expanding like the first 5 terms or the entire thing, we're going to find a specific term. All right, so here in example 3, we are to find the 8th term in the expansion of a plus b to the 11th power. So the process of finding this, there's maybe different ways you can approach it. What I think is the simplest way is you find the exponents with the variables. So you find the exponent for a, then you find the exponent for b, and then use those exponents to find the coefficient. All right, so to begin, to find the exponent for a, we have to realize, first of all, how many terms total are there in this expansion? Well, we kind of alluded to this earlier, but even though the exponent is 11, we actually have 12 different terms. And you can think through maybe if you had just a plus b to the first power, realize that that would be a plus b, so there's 2 terms. And if you had a plus b squared, and you expand that, you get a squared plus 2ab plus b squared. So if the exponent is 2, we have 3 terms. So if you forget that we have one more term than the exponent, you could just think through these examples, or realize that we start with a to the 11th power, and then we have the 10th power, 9th power, 8th power, etc., all the way down to a to the 0 power. All right, so the exponents range from 0 to 11, meaning that would actually be 12 different numbers starting with 0. So all that to say, we have 12 different terms. So to find the 8th term in this expansion, we define the exponent for a. We would have to take 12, because there's 12 terms, and then subtract 8. That gives you the exponent. So it's 12 minus 8, or 4, for the exponent. So that becomes a to the 4th power. Now to find the exponent for b, what we have to realize is that our exponents for a and b must always add to equal 11. So if a is to the 4th power, and we have b next to it, b must have an exponent of 7, because 4 plus 7 gives you the 11 that we have right there. All right, so we now have a to the 4th, b to the 7th power as the variable component of the term. Now from here, we can use those exponents to find the coefficient. So the coefficient of any term is found by taking this 11, or whatever the exponent is. You take that and make it a factorial, so 11 factorial, and then divide that by the exponents with the variables factorial. So we have a to the 4th, b to the 7th power. We take the 4 and 7, make them a factorial, and put them in the bottom. So your coefficient would be whatever that is equal to, 11 factorial over 4 factorial times 7 factorial. Now if you look just at the 11 and 7 factorial right here, we have 11 times 10 times 9 times 8 times 7, all the way down to 1. 7 factorial is 7, 6, 5, all the way down to 1. So starting at 7, all those numbers would cancel out. So what you're left with is going to be 11 times 10 times 9 times 8. And then don't forget the 4 factorial in the bottom. You have 4 times 3 times 2 times 1. And we see that typed up over here in the notes. And you could take the time to multiply the 11, 10, 9, 8, and then divide by 4 times 3 times 2. And that number is going to be 330. So then to put it all together, we have the coefficient is 330. The variables are a to the 4th, b to the 7th. So your 8th term in that expansion would be 330 times a to the 4th power times b to the 7th power. So now we have another example, example 4. And this is just an extra practice problem that you can go through. So it's the same type of problem as example 3. So if you want, you can try to do this one on your own. And then once you've tried it, you can play the video from here to see if you got it correct. All right, so for this one, for example 4, we want to find the 13th term in the expansion of a plus b to the 15th power. So to begin, we want to find the exponent for a. And we do that by realizing that if there's a 15 here for the exponent, there's actually 16 terms. And if we subtract 16 minus 13 for the 13th term, that will give us our exponent. So a will be raised to the 16 minus 13, or the third power. And then from here we can find b. So if a cubed is the a component, and then we have b multiplied with that, we know that the exponent with b must add with a 3 to give you 15, this number up here. So b would be raised to the 12th power. So we have now a cubed, b to the 12th power. Now the last part is to figure out what number goes in the front. What is your coefficient? So to find that, we take this 15, make it a factorial, and then we divide by 3 factorial and 12 factorial, those exponents with the variables. And now from here, we just need to simplify. So if you simplify, realize that the 15, we have 15, 14, 13, 12, 11, all the way down to 1. 12 factorial is 12, 11, all the way down to 1. So the 12, 11, 10, 9, 8, etc., all the way to 1 will cancel out, and you're left with 15 times 14 times 13 on the top. And then don't forget this 3 factorial, which is 3 times 2 times 1. So we now have 15 times 14 times 13, divide by 3 times 2 times 1, and if you work through this correctly, your coefficient is going to be 455. So to put it all together, we have 455 times a cubed times b to the 12th power. So this here would be your 13th term of that expansion. So we have stated that the expansion of a plus b to the 15th power would be right here, 455 a cubed b to the 12th power. Now what if you replace the a and b with something different? What if a, for example, were 2x, and the b, for example, were 1? So you have 2x plus 1 to the 15th power. So that's what we see right here in this next slide. So again, we have this statement that we already concluded earlier in the last slide. And all we do is we simply replace the a with 2x, and the 1 is replacing the b. So replace a with 2x and b with 1. So if you do that, and you replace the a and b right here with 2x and 1, we now have 455 times 2x cubed times 1 to the 12th power. All right, so then 2x cubed, we have 2 cubed is 8, and then we have x cubed, and then 1 to the 12th power is just 1. So we have 455 times 8 times x cubed. And then 455 times 8, that would equal 3,640. So the 13th term in this expansion would be 3,640 times x to the 3rd power. Now to finish off, we've learned in a previous lesson about what we call sigma notation or summation notation. So we showed in the first slide of this lesson that a plus b to the n power is represented by this sum right here. Now we can express this, we can simplify this with summation notation. All right, so if we want, we could write this as a sum. So we have our summation notation right here. And what we want to do is actually, we want to start this off with a 0. It's like the 0 term, and then 1, 2, 3, etc., all the way to n, some number. All right, so the reason we chose that is because we can see the pattern a little easier with the term number, so with the term number, and with the coefficients, and with the exponents. All right, so as you set this up, we have, let's use the letter k. So we use the letter k, k equals 0, because we start with the 0 term, go all the way to n, some term number over there. So this would be k equals 0 to n. Now from here we want to figure out a pattern with the coefficients and then with the variables. All right, so with the coefficients, notice that the numerators for the coefficients will always be n factorial. even with this first term, remember we said that is the same thing as n factorial over n factorial over 0 factorial, right? So that can be expressed in that manner. So the numerator will always be something factorial. And it's going to be n factorial. All right? So whatever n is, the exponent, that's going to be written as a factorial. So the numerator is n factorial. And then the denominator, notice we have n minus something. So that something is changing each time. So look at the changing part. We have 1, 2, 3, etc. Notice that corresponds with the term number. So we have n minus the term number, right? And the term number, we're using letter k for these different numbers here. So we're going to do n minus k. All right, and that's factorial. Times, and then notice we have 1 factorial, 2 factorial, 3 factorial, etc. That is the same number as the term number up here in the top. So that would be k for the term number, k factorial. So again, k is representing the term number. All right, because normally we use n, right? N is the term number, but here n is in the formula, so we don't want to use n twice. It wouldn't make sense. So we use a different letter. We're going to choose k. So that would be our coefficient, and then we have our variables. So we have a to some power, and then b to some power. So looking at the a, okay, notice we have n in each of these, and it's going to be what? N, look at the changing part, n minus 1, minus 2, minus 3. Notice that corresponds with the term number. So we take n minus the term number, so n minus k. All right, and then the b, the variable b, notice the exponent, and actually this should be b squared, sorry. Exponent will be 1, 2, 3, etc. And that exponent with b corresponds with the term number, right? 1 is the exponent, 1 is the term number, 2, 2, 3, 3. So the exponent for b is going to be the same as the term number. We use letter k for term number. So this would be b to the k power. All right, so that would be it. So this expression right here, this summation notation, represents the summation of any binomial expansion. So a plus b to any exponent. So a plus b to the n power can be represented with this sigma notation. And that concludes our lesson for today. We will see you next time.